before the break, I talked about the rationale behind the use of path integrals in the context of quantum mechanics or quantum field theory. Now, let us try to understand what exactly we mean by path integrals. Before we talk about path integrals, let us have a look at contemporary or standard conventional integration, how it is carried out. Let us say we have got a function y is equal to f x, and we need to integrate this function y is equal to f x between the limits x a and x b. What do? We take a very thin strip of length of thickness dx along the x axis, and of the value of y along the strip, along this thin strip, is assumed to be constant, and we assume it to be the initial value, that is f of x a. So, the area of this thin strip then works out to f x a, which is the height of the strip, the value of y, that is f x a, that is the height of the strip, multiplied by the thickness, that is dx. And then we consider the next strip. For the next strip, again we take the initial value of y as the constant value over the thin strip of dx, which is the next strip. We divide the entire interval x a to x b into thin strips of thickness dx. So, we are now talking about the second strip of thickness dx. The height of this strip would be f x a plus dx, and obviously the thickness would again be dx. So, again the area would be f x a plus dx into dx. In this way, we continue up to the point we reach x b. And then what we do is, we do a summation of this, which is given here. If you look at it carefully, this is what the summation is. Summation I equal to 1 to n f x I and dx I. And now what we do is, we squeeze the thickness of the strip to very, very small, infinitesimally small, and that is what we mean by integration. So, limit n tending to infinity. If n tends to infinity, what is n? N is the number of strips. So, if the number of strips is tending to infinity, obviously the thickness of each strip will tend to 0, and in the limit that the thickness of each strip tends to 0, the integral f x, the summation f x I dx I translates to the integral f x dx, which effectively is the area bounded by the ordinates at x equal to x a, x equal to x b, and the curve y is equal to f x. This is the definition, this is the meaning of the concept of integration, conventional integration or standard integration. This is another example where we are trying, there we worked out the area, here we are trying to work out the length of the curve. And again we have this formula, integral x a, x equal to a to x equal to b dx, and ds is now assuming that this during this strip the Pythagoras theorem holds, and therefore, ds square is equal to under root dx square plus dy square, that is in two dimensional Euclidean space. So, that is simplified, and we again get the length of the curve. So, this is what conventional integration is. Now, the basic thing to note here is that the strips are assumed so small that in the integration process, the strips are assumed to be so small in thickness, that in that range the curve may be approximated by a straight line. Therefore, we can, in other words, we can say that the entire curve is comprised of a pattern of infinitesimally small straight lines. Now, we talk about functional integration or path integration, but before we talk about path integration, let us understand the concept of function of a function. I illustrate it with an example. I believe most of the viewers would be familiar with basics of physics, at least at the graduate level, and therefore, you would be familiar with classical mechanics and the concept of Lagrangian mechanics and Hamiltonian mechanics. You know that the Lagrangian of a physical system is a function of, in configuration space, it is a function of the position of the system and its velocity. It can also be an explicit function of time, but for the moment we exclude that possibility. By and large, for most systems, we model the system by a Lagrangian which does not contain or which does not have explicit time dependence. So, in those situations, the Lagrangian is a function of q. Q is the generalized coordinates and q dot, which is the generalized velocities. Now, this is what the Lagrangian is, but as you know, q is the position of the system, and the position of the system itself is a function of time. Obviously, the system evolves as time moves forward. Time is the indexing set. In fact, time is an index, whereby as time increases, the position of the system changes, and correspondingly, obviously, the Lagrangian will also change. So, the Lagrangian is therefore a function of a function. Let me reiterate, Lagrangian is a function of position and velocity, and the position and velocity themselves are functions of time. Therefore, the Lagrangian becomes a function of a function. The relevance of this definition will become apparent later. Now, this Lagrangian is a function of a function. We can integrate this Lagrangian between t1 and the initial time at which the system starts evolving to the point at which its evolution is to be traced. In fact, this particular expression, if you recall, is nothing but the action integral. So, the integration of the Lagrangian between the initial time and the final time T I and T f will yield a number, and that number is called a functional. So, what is a functional? As far as our restrictive definition, I will come back to it. As far as our restricted definition of a functional is concerned, a functional is the integration or is the integral is a definite integral of a function of a function. Now, obviously, the function depends on the Lagrangian. It also depends on the form of q t and q dot t, and finally, it also depends on the integration limits t I and t f. So, the functional that is the integral f or the action integral in our case, in the special case when this is the Lagrangian, the action integral depends on the Lagrangian itself, on the form of q or the dependence of q on t, and finally, the two limits which constitute the integration limits. The important thing is this functional that we are getting on integration is a function is dependent on the path followed by the system. For each path you return a different value of the function f or the action integral. Let us see, this is portrayed in the diagram. For simplicity, we assume that L is only a function of x. We ignore velocities for the moment. This is a 3-dimensional space. X t is along this axis, y t is along the y, L x t is along the y axis, x t is along the x axis, and time is along the z axis. Time is along the z axis, x t is along the x axis, and L x t is along the y axis. Now, the first thing is, let us look at this. The first thing is, as time evolves, x t is also evolving. X t is a function of time. Now, the relationship as t moves from T A to T B of x t is given in the horizontal plane, that is the x dash t plane, and that is given by this curve. This curve, let us call it A B. This is a curve that lies on the x t plane. Now, corresponding to each value of x t, now L x t is a function of x t. Therefore, corresponding to each value of x t, that x t takes on this path, x a b, we will get a value of L x t. For every value of x t, we will get a value of L x t, and that is depicted by this dark curve in the 3-dimensional space, where we have time moving from, because L is a function of x, which is a function of t. As time evolves, x also evolves, and as x evolves, L x t is captured by this particular curve. But the integration has to be performed with respect to t. Please note this, the integration is with respect to t, it is not with respect to x. So, because the integration is with respect to t, we need to take a projection of this x of this Lagrangian curve on the L t plane, on the this is the yz plane or yz plane. On this we get the projection of this in this Lagrangian, and then we do this integration as we did in the earlier case. This is the curve in this 2-dimensional space, the projection of this in this 2-dimensional space, and we will get this area as the shaded area as the net result of this integration. This is the functional. Clearly, the important thing is this function, this area which is this integration, is a function of this path. If the path were to be different, on this on the horizontal plane, on the tx plane, if the path were to be different, clearly the Lagrangian would have been different, and the projection of the Lagrangian would have been different, and obviously the value of the functional would also have been different. So, every path returns a different value of the functional. So, as far as the mathematical definition, the broader definition is concerned, a functional is a function of a vector space to a scalar field. A functional maps a vector to a scalar. Now, as far as the equivalence or the relationship between the two definitions that I have just explained, well, the paths q t themselves form a vector space, and the integral of L x t is a number, and which forms a number field or which forms a scalar field. So, the enumeration of the example that I took of the Lagrangian is very much within the mathematical definition of a functional. The paths x t form a vector space, and the integration or the integral is a number, and therefore a scalar field, and the equivalence is pretty much clear. You are mapping a vector into an element of a vector space into an element of a scalar field. Now, the geometry of path integrals are representing sum over all paths. I will come back to it in just a minute, it will be more clear. You see, I just now mentioned that every path returns a different value of the functional. Let us go back to the diagram. Every path returns a different value of this functional. So, if you have a number of paths, you will get a number of values of these functionals. Now, if you choose, for example, just keep at the backdrop of your mind that when we talked about quantum mechanics, we talked about the path, the 2-slit experiment, we ended up with the conclusion that the the amplitude of a point on the detector screen O would be the sum of the amplitudes of all possible paths from the source to the detector screen point under reference, that is O. Then so we need to sum over a number of paths, and each path, as you know, each path gives rise to a functional on integration. The integration, that means what? That means we may need to integrate over a number of paths. Integrate this as LXT or some other function which we will come to, but we need to integrate it over all paths. So, that part, whereas it is the integration of a functional. First you are having a functional, this is this integration of this LXT, this particular f is already a functional, and now what you are doing is you are integrating this functional over a number of paths, because this functional itself is a function of the path. So, if you have a number of paths, you will get number of values of this functional. So, if you want to have a sum of all this number of values of the functional, you need to integrate it, if it is a continuous variable for that matter. So, that integration is called path integration, or also called functional integration. Now, go back. So, path integrals are integrals representing sum over all paths satisfying some boundary conditions. That you have a functional, you are integrating that functional. So, they can be understood as extensions of to infinite number of integration variables of usual multidimensional integrals. Here again a clue is given. You see, when we talk about quantum field theory, we are essentially talking about infinite dimensional, infinite degrees of freedom. So, we need to talk about mechanisms which are compatible with managing or handling the mathematics of infinite degrees of freedom, and that is why this particular statement becomes relevant or comes into relevance. So, a functional is a definite integral, but because a functional is a path dependent, if you want to have a sum of functionals corresponding to different paths, that is what we call a path integral. Now, if you look at these are some illustrations. If you look at this, the integral number 2, you have a functional f and you are integrating it between two values qi and qf, and this is the path integral measure, capital D qt in square bracket. This is the path integral measure. So, f integration between qi and qf with respect to dqt is a path integral. Similarly, instead of f we can have a function of f and then integrate that, which is given in number 5, where we are integrating L dt. Here you look at this, we are integrating exponential I f. We have talked about f is integral L dt, recall that, and we are integrating a function of a functional, and then we are integrating that. This is again our integration measure, the path integral measure that we have for integration. Now, the cardinal applications of path integrals, as I mentioned several times, are in the field of quantum mechanics and quantum field theory. Briefly, I touched upon heuristically. I touched upon why path integral becomes relevant, because we are talking about the summation of amplitudes over an infinite number of paths covering from the source to the destination of a particular physical system. Now, however, when you come to more rigor as we move along this course, you will understand more about this. These are the quantities of interest when we talk about physical systems, quantum mechanical systems, that is. For example, this particular quantity gives you the transition amplitude, that is, it gives you the amplitude from which we can work out the probabilities. amplitude from, it is not the probability itself, it gives you the amplitude from which you work out the probabilities by taking the absolute value squared, and this is given by q. This particular expression represents the transition probability of a quantum state q dash t dash of a physical system moving into a quantum state q double dash t double dash, and it is given by the path integral over phase space of what? Of this exponential. This is a weight factor which is there. You will see here in every case this particular quantity appears. We will talk about from where it comes, but it is there. If you look at it, S is what? S is the action integral. It is integral L dt. So, S is the action integral, and exponential of I s with I upon h into s is the weight factor which is used whenever we talk about calculating quantities which are of relevance in quantum mechanics. What is the second quantity? This second quantity is operator q t 1 sandwiched between two states, and similarly this is the ground state. Ground state, the third quantity, is the ground state expectation value of the product of field operators phi z1 to phi zn, and all these are given by functional integrals. There is another very interesting observation. See, let us go back for a minute. If you look at this quantity, what is its modulus? If you look at this quantity, the modulus of this quantity is 1. So, in that sense it does not really contribute to the integral, but however it contributes in the form of a phase. Then we on the basis of this we can also explain why physical systems for which h tends to 0, that is s upon h tends to infinity, why in such physical systems the behavior is modeled adequately enough by classical paths or classical behavior, and the quantum set of paths translates to or approaches the classical path. See, the point is, in the case of systems that have that are highly fluctuating, the fluctuations tend to cancel each other, and as a result of which the fluctuations which are more or less close to the classical path tend to reinforce each other, and we tend to observe the classical path. That is what is the inference that is usually in fact it is given a name also. It is called the Ehrenfest theorem, that by and large it can be quantitatively proved in fact that classical paths tend to predominate over the entire set of paths even in a quantum system. The paths that are far away from the classical ones tend to fluctuate more, and therefore they tend to cancel each other, whereas the leading contributions come from the classical paths. Okay, some prerequisites. Before we get into the course proper, it is important to understand or important to acquaint the viewers with some prerequisites. I think these are some fundamental points that fundamental concepts that I would like to touch upon, though briefly, so that whatever follows is the course forms a complete wholesome course in itself. Some basic things about probability to the extent that would be required for us. Gaussian distribution forms the cornerstone of the entire path integral formalism. Normal distribution or Gaussian distribution is fundamental in literally the entire path integral approach to quantum mechanics. Then we have the Brownian motion. The Brownian motion forms the golden thread that relates statistics to physics. Simply stated, it is an unbiased random walk, and we shall be exploring that, although to a minimal extent, to the extent which we are going to use further. A bit of central limit theorem, which is again a very beautiful theorem, and then a brief touch on green functions. Green functions again, the correlations that I talked about, the correlations that these turn out to be green functions of the various quantum mechanical equations, like the Kleene-Gordon equations, the Schrodinger equation, and the Dirac and Gauge equations, and therefore we need to understand a bit about green functions. So, talking about probability, the most important thing is the sample space. The sample space constitutes the space of all possible outcomes of a random experiment. A random experiment is an experiment whose outcome is not perfectly predictable, whose outcome is not predictable with certainty, and as a result of which what are the various possible outcomes can be enumerated, and that constitutes the sample space. A random variable is a mapping. It is a mapping from the sample space to the set of real numbers. In other words, it allocates a real number to each possible outcome of a random experiment. Whatever are the random outcomes of the random experiment, each of them is assigned a number, and this mapping that does the job is called the random variable. So, it is a mapping from the set capital omega, which is usually used to represent the sample space, to the set of real numbers. X goes from omega to r, and this omega is for some possible outcome, and this omega is given a number which is some real number x, small x. For example, if we write x equal to small x, what we precisely mean is, that means x of omega is equal to small x. In other words, that the element small omega of the sample space capital omega is assigned a real number which is small x by the mapping which is capital X. Now, we can have discrete and continuous random variables. Clearly, the domain of the random variable is the sample space, but the random variable can be a mapping to a discrete set, or it can be a mapping to a continuous interval. For example, if you have a toss of a coin and toss of 3 coins, say, and you count the number of heads as the random variable, then the random variable is a discrete number. It can either be 0, it can be 1, or it can be 2, or it can be 3. So, this is a discrete random variable, and continuous random variable, for example, the average age of students in a class, it is a continuous random variable, where the mapping is to an interval between 2 points on the real line. Now, in the case of discrete random variables, we define a quantity called the probability mass function. The probability mass function gives us the probability of occurrence of a particular outcome out of the set of various possible outcomes listed in the sample space. Similarly, in the case of continuous random variables, we have a quantity, a parallel concept called the probability density function. We will continue from here in the next lecture. Thank you.